Hi guys. So in this video we're going to talk about weak convergence of sequences in the Hilbert space. And we're going to let H with its inner product be a Hilbert space, and let a sequence UN be in that Hilbert space. We say that the sequence UN converges weakly to some U in H if for every Z in H we have this, that the inner product with UN and Z tends to U with Z as n tends to infinity, and this is written as UN and then the arrow with the bottom half missing. So this means that UN tends weakly to U or converges weakly to U. So the reason why this is weak is because strong convergence implies weak convergence. And the proof of this is very simple. We just use the Cauchy-Schwarz inequality. So if we have the inner product of UN minus U with Z, where up here we've just taken this over, so this thing should tend to 0. This thing is less than or equal to UN minus U, the norm of that, times the norm of Z. And if UN tends to U strongly, then this thing goes to 0. So this thing goes to 0, hence UN tends weakly to U. Now for some examples, we'll do some very simple ones. So we're going to say let the phi-ans be an orthonormal sequence. And that just means, this just means phi n inner product with phi m is equal to 1 if they're the same, 0 if they aren't. Then that just means that the phi-ans will tend weakly to the 0 function or the 0 vector in the Hilbert space. So to prove this, we'll need Bessel's inequality. There's other ways to do it when you have the exact form, but this one works in general. So if this is given an orthonormal sequence, the following inequality holds. So the sum from n equals 1 to infinity of the inner product of the phi-ans with some z. So the inner product of phi-ans with z squared and then summed up. This is less than or equal to the norm squared of z. And this is for z in your Hilbert space. We know that the sum is bounded above. The sum itself is made up of terms that are non-negative. That means that by the monotone convergence theorem, this thing must converge. So that means all the terms in here have to go to 0. And that just means, after all of that, you determine that phi n comma z in a product z, the norm of that squared tends to 0, and then square rooting and then undoing the inner product, we determine that phi n comma z in a product, that goes to 0, but the only way that this thing could be 0 is if the phi-ans are tending weakly to 0, because this thing is equal to 0 comma z. Because remember, this thing has to hold for every single z, so anything that means z isn't 0 It just means that these have to tend to 0. So if we let our Hilbert space be little l2, and we say phi1 is equal to 1, 0, 0, so on, phi2 is 0, 1, 0, 0, so on. So phi n is just zeros up until the nth place, and then zeros after. This is an orthonormal sequence, because if you take the dot product with itself, you'll just get a 1. If you take a dot product between other things, you'll get 0. And that means that this sequence, because it is an orthonormal sequence, must tend weakly to 0.